Okay, so we're going to prove this theorem here. And I'm just calling it radius bisecting a chord theorem. And what it states is following. It says that if a radius bisects, we need to know what this word means, bisects a chord. We need to have an understanding of what a chord is, right? Then the radius is perpendicular to the chord. Okay, perpendicular, right? Don't forget, the upside down T means perpendicular. What does perpendicular mean? They intersect at right angles. They intersect at 90-degree angles. Same statement. So here I have if a radius bisects, that means cuts it into two congruent parts. So if a radius cuts a chord into two congruent parts, then the radius is perpendicular to the chord. Now, what's a chord? A chord is any segment of the circle that goes from one end to the other, right? So this is a chord, for example. This is a chord AB. So it just is the segment joining 2 points on the circle. So A is a point in the circle, B is a point in the circle, so then this is the chord AB. And again, if I have it where it cuts, the radius is a radius CE. If a radius bisects the chord, then we know that the radius and the chord are perpendicular to each other. So I rewrote the statement like this. We should see that this statement here is essentially the same statement as the original, but just written in general to fit into this diagram. So CE is a radius, that's obvious. C is the center of our circle here. And DB and DA are congruent. That just says that CE bisects AB, right? So I used a bit of a definition here, right? I skipped a step in this theorem here by using the definition of bisects. I said, I give you right away that this segment, this half, is equal to this half, right? The radius bisects the chord. Then, if that's true, I know, then immediately that the radius and the chord are perpendicular to each other. Now, how do I know this? Let's go through the proof. So I know that, what do I know? I know what's given, so let's write down what's given. So let's do our statements and reasons. So statements and then reasons. One, let's write down what's given. What's given is that C is a radius. Okay, we don't really need to write that, but I will write down what's given here. And I know this because it's given, but it's really given to me as the definition of bisects from the original. But it's okay, we'll just write it down as our given, like that. And I have that this segment, BD or DB, is congruent to this segment, DA or AD, whatever you want to call them. Okay, those two segments are congruent. With that, I'm going to write in two radii. So the two radii I'm going to write in CA and CB. And I'm going to immediately call them congruent to each other. And I'm going to write that in. I'm going to say CB is congruent to CA. And why is that true? That's true because they're both radii. So both. Yeah. both are radii. Both are radii. Now, if we look at this, and let's look at this figure here. So now I have that this segment is going to be congruent to itself. This DC, if I didn't mess that up. So this DC, this is point D over here. This little line, DC, is of course congruent to itself. So what's the statement that I could say here? What I can say here is that triangle D, right? Again, this is point D right here. DBC is congruent to... Oh, wait, before I do that, I need to state a redundant statement. Let's write the redundant statement. The redundant statement is that DC is congruent to itself. Reflexive. And now I can talk about what I wanted to originally. So now I can say triangle DBC is congruent to triangle DAC. And that's because of side, side, side. 5. Now I have that these two triangles are congruent. So let's look at this picture now. Now I have this here. Right, let's just pull out this big triangle. So let's put it in a color I haven't used. This big triangle, just so you guys can see, I'm pulling it out and I'm putting it over here. And you guys should see that it looks like this, right? Where this is point D, this is B, this is C, and then this is A. And what we should convince ourselves of is, first, that angle BDC is congruent to angle ADC. Okay, so why is that true? I know, right? I know that this was congruent to this is congruent to itself, and these two are congruent because they're both radii. So I showed that these two triangles, the left triangle is congruent to the right triangle. That means that all the corresponding parts are congruent. So this angle, let's call it angle 1, is congruent to angle 2, right? That's angle BDC. That's angle 1 is congruent to angle ADC because those two angles correspond. I'm just going to write it as angle 1 is congruent to angle 2, CPCTC. Corresponding parts of a congruent triangle are congruent. 6. Now you should convince yourself that, well, I really should write a redundant statement. Let's just write that the measures of these two angles are equal as definition of congruent angles. 7. Now let's say something of value. Let's say that we know that these two angles form a straight line. So I know measure of 1 plus measure of 2 is equal to 180. And we say form a straight line. 8. Now, instead of me writing measure of 1 or measure of 2, it doesn't matter which one I pick, but instead of me writing measure of 1 here, I could write measure of angle 2, and then that'll be measure of angle 2 plus measure of angle 2 is equal to 180, which is the same thing as 2 times the measure of angle 2 is equal to 180. So I'm doing a lot of the algebra. Let's do the algebra on the side very quickly. This here, right, if I wrote measure of angle 2 instead of measure of angle 1, I'd get measure of angle 2 plus measure of angle 2 is equal to 180. But then that means that 2 times the measure of angle 2 is equal to 180. And I get that the measure of angle 2 is 90 degrees. And that's what I'm going to write right here. Measure of angle 2 is equal to 90 degrees. I'm going to put the reason for that is substitution with some algebra. So I just did some algebra. Let's just write that I did some algebra to get that last result. Now, I have that measure of angle 2 is 90 degrees. That's this one right here. And I know that it's the same as measure of angle 1. So CD, this line, CD, and this line formed a 90-degree angle. That means that these two lines are perpendicular. And I'm just going to write that. You just fill it in at the end. You just write CD is perpendicular. So let's see if I can do this. CD. Let's see. CD is perpendicular to AB. And that's definition of perpendicular. Definition of perpendicular. They formed right angles. Okay? My pen died. They form right angles. So then, therefore, they're perpendicular. And that shows the theorem.